Thanks. Thanks everyone for coming. So I'm going to be talking about subroutines, which are very natural in classical algorithms, and we also use subroutines a lot in quantum algorithms, but some of the things that we take for granted in the classical setting are a little bit trickier in the quantum setting. And in particular, I want to talk about how subroutines compose and what the resulting complexity of a composed algorithm is. And I'm going to talk about composing subroutines into arbitrary quantum algorithms. And I'll also briefly state a result that's specific to composing subroutines into quantum walk algorithms at the end. So to set the scene, let's consider classical subroutine composition. So suppose you have some classical program, which could, for example, look like this, that makes calls to some subroutine, meaning that you have some other piece of code written somewhere else that you call multiple times from your main program. And this sort of thing is extremely useful because it allows you to abstract some functionality that you call multiple times. But more importantly, it also allows you to use existing solutions to sub-problems of the main problem that you want to solve so that you don't have to reinvent the wheel each time. And a motivating example that you can keep in mind is evaluating an unbalanced formula like an AND of n bits, each of which is the OR of some block of the input. And we don't assume that each of these ORs is on the same number of bits. So here we're supposing that the first OR is on the first K1 bits in memory, and then the second OR is on the next K2 bits. And it would be very natural here to, just have a subroutine that computes the OR, and your main program will just call the subroutine on each of these n blocks of the input. But this is just one example. Of course, this code could be for anything like breaking a crypto system or simulating fluid dynamics or some stock market thing. This could be absolutely anything. So it's super useful to be able to do this in practice. And it's also very straightforward to analyze such a composition. So if the expected running time of your subroutine is E of ti, and here I mean expected in whatever randomness your subroutine uses, if any. It might, of course, be deterministic. Then we can compute the expected running time of the full program like this. So here, L represents the the number of operations of the main program that are not involved in subroutine calls. So for example, this comparison of y and 0 here, which is called n times in this particular example. And then we add, for every I that is a possible input to the subroutine, we take the expected running time of the subroutine on input I, and we multiply it with the expected number of calls to the subroutine on input I. We add this up for all I. And I think, I hope you'll agree that, this classical composition result is extremely straightforward. There's nothing kind of clever or deep going on here. This is just a very straightforward analysis of how things compose. And so, it's somewhat surprising, given how obvious this is for classical algorithms, that a quantum analog of this statement actually does not hold in what we call the zero error setting. So that's the setting where we require that the algorithm always outputs the correct answer. So even though this result is, very, very easy to see in the classical world, it turns out that in the quantum world it does not hold for zero error algorithms. However, something we can always do if we have an algorithm with this expected running time, classical or quantum, let's suppose it has zero error, is we can say, we're going to run the algorithm big O of the expected number, the expected runtime steps. So let's say 10 times the expected runtime, and then we're going to stop and output something random. And this will always give us a bounded error algorithm. So an algorithm that now, we can't assume that it makes no error, but maybe the error probability is at most 1/3. And this is just by Markov's inequality, because if we run this for 10 times the expectation steps, then we've probably stopped and output the correct thing, and otherwise we'll just output something which may be wrong, but this happens with very low probability. So this is the bounded error setting, which is also the more commonly used setting in quantum algorithms. And the main result is that we can get a quantum analog of this obvious classical composition theorem for bounded error quantum algorithms. And what I mean by a quantum analog of this result is that both the main algorithm as well as the subroutine can be quantum, meaning that, for instance, we can call the subroutine on a superposition of different inputs I. And, well, okay, but what do I mean then in the quantum analog by the expected number of calls to the subroutine on input I? Because, as I said, we can call the subroutine on a superposition of different I. Well, you know, you may have noticed that I expressed the expected number of calls to the subroutine on input I as a product of two things, which I did not explain. So here, Q, which does not stand for quantum, but rather query, is the number of times your main program calls your subroutine. And then PI bar is the average over all calls to the subroutine, the probability that that subroutine is called on input I. And in the quantum analog of the statement, we just replace probability with something called query weight, which I will define more precisely when I've given a little bit more detail. So this is our main result, is this quantum analog of this, you know, pretty obvious classical result. And, you know, now I want to go into a bit more details about what I mean by the quantum analog of this. And I also want to kind of highlight a little bit like why quantum composition isn't obvious. So we saw that this classical result is completely obvious, and I hope you believe me that this is not obvious for quantum algorithms, since I told you that it actually does not hold in the setting of zero-error algorithms. But you know, it's I hope I can also show you a little bit like why this is so difficult in the quantum world. So if we have a quantum program, the usual way that we view it is as a quantum circuit, which is a secret of unitaries, Vj, and usually we think of these as being from some set of whatever we want to consider our basic operations. So, you know, they might be elementary gates, maybe acting on, not acting non-trivially on only one or two wires, for example. But if we design a quantum algorithm, we can also use subroutines, meaning that some of the steps of the algorithm we assume are implemented by a subroutine. And it's natural to assume that the input to the subroutine is on one particular wire. Let's say it's the first wire. And then we can suppose that the subroutine is controlled on this wire. So the value of this wire controls the behavior of the subroutine. And then what does an implementation of the subroutine look like? Well, it's just going to be itself a circuit, which will just have some number of gates. And the idea is then that if you take a copy of this circuit and plug it in, for each of these sort of subroutine placeholders, you'll just get one big circuit. But notice here that the number of operations in the subroutine T is independent of the input I. And that's sort of necessarily true, because we're going to call the subroutine on a superposition of different I's. And so even if you have an algorithm here that terminates early for some inputs, it's unclear how you could take advantage of that, because even if you terminate early in one branch of the superposition, it seems like you have to wait for every branch of the superposition to terminate before you could apply the next unitary. So in our motivating example, where we have an AND of ORs, you know, it's natural to suppose that we implement this by having some main algorithm that is Grover's algorithm to compute the AND. So we're searching for one of these n bits that is 0. So we're just going to have like a square root of n repetitions. Every second one is a call to a subroutine that computes an OR. So this subroutine is going to compute the OR. Let's say it's also doing so by Grover's algorithm, where I tells you which part of the input to look at. The ith block of the input is ki bits, and so we know that we should be able to implement the OR of ki bits in square root of ki steps. But again, it's unclear how we could make use of the fact that the square root of ki might be much smaller for certain I, and you know, naively we actually have to have our subroutine have max over I square root of ki steps, which gives a total cost of square root of n times the maximum over I of square root of ki, since we call the subroutine square root of n times. And unfortunately, it's known that this is far from optimal. There's actually a quantum algorithm that can evaluate a circuit or a formula like this, where in a complexity where we replace this maximum with a kind of average. But that algorithm is just, you know, it's not using any kind of composition of and an or. It's rather like some quantum walk algorithm that's for evaluating formulas. And if we wanted to kind of reproduce this result, but in some way that just uses circuit composition, what we would really want is for every I that's a possible input to the subroutine, a different circuit where these circuits could be of potentially different lengths. but it's then unclear now if you have one different circuit for each input, like how you would compose this into your main algorithm if you just look at these straightforwardly as circuits. But we do in our main result we managed to somehow combine all of these circuits to get a better composition result. So I will now restate the main result with a little bit more detail now that we've seen what these things mean. So the main result is that if we have a quantum algorithm that calls a subroutine, where we can express the subroutine as sort of one circuit for every possible input to the subroutine, we can combine these to get this composition results, which we can compare with a naive composition, where here L is the number of operations in the main subroutine, Q is the number of those operations that are queries, and Ti is the number of operations in the subroutine when called on input I. And as I said before, naively we have to sort of wait for the maximum, wait for the subroutine to have terminated on any input before we can move on. And so we get a max here, and in our new composition result, we replace this maximum with some weighted average. And also, it's not shown here, but we can also handle the case where the runtime of the subroutine is a random variable, and then we get an expectation here. So this is a weighted average where this QI bar is something called the average query weight, which we can now define precisely. So if we let psi t be the state before the tth query, so here right before we apply the first query, we could call that psi 1. Then QIT is the query weight on input I at the tth query, and this is the probability that if you were to measure the state just before the tth query, you would get an I in the input register. So this is like the quantum analog of the probability of querying I in the tth subroutine call. And then QI bar is just the average over all Q queries of the query weight on input I. Okay, so this is our sort of main composition theorem. I sort of tried to convince you that it's not really obvious how you could sort of combine these this subroutine, which varies in length from different inputs, into this circuit. But we do manage to do this by basically taking sort of our main algorithm and our subroutine, which we express as n different circuits, and kind of chopping them up and recombining them in some way. And I want to spend now like most of the rest of my talk giving a very, very cartoon explanation of how this is done. So this is going to be really at a high level. So maybe just kind of relax and don't worry too much about the details. So here, we're going to take inspiration from quantum walk algorithms. And actually, as I mentioned at the beginning, we do have a composition result specific to quantum walks, which I will state very quickly at the end. But for now, let's just take some intuition from the picture of quantum walks. So in a quantum walk, or a random walk on some graph G, we can imagine some probability that starts in some initial distribution and sort of propagates through the graph until we get to some marked set or some vertices corresponding to solutions. And in quantum walks, we can associate with every vertex a one-dimensional subspace. If you work in quantum walks, this may look familiar to you, but please also feel free to just ignore all formulas in this cartoon picture and just look at the pictures. So I just want to say, like, let's think about quantum walks as just like probability propagating through a graph to some final states. Okay, now, on the other hand, if you have any quantum algorithm, I want to claim that we can sort of, from this quantum algorithm, get a line graph where every vertex corresponds to some space that represents a step of the algorithm. And these spaces might look familiar to you, but again, don't worry too much if not. And I also want to claim that sort of you can kind of imagine that the running of the algorithm involves some probability or flow or of some kind propagating through this graph, starting from some initial state and kind of like running through the steps of the algorithm to get to some final state. So I want you to think of a quantum algorithm as like some sort of a line graph with a vertex for every operation. Okay, so just please believe me that that's a reasonable thing to think. And now, like looking back up at this top box, when you want to implement a quantum walk or a random walk, something that you have to be able to do is take a step on the graph. So you need to be able to, like, for instance, step from V to V prime, and that could be computationally difficult. So, like, let's imagine that transitioning from the state V in this graph to the state V prime is difficult, so you actually need some kind of quantum algorithm to implement this step for you. And as I claimed with any quantum algorithm, for that particular algorithm that implements a step from V to V prime, you get some line graph. And we can think of this line as implementing this edge of the graph, and graphically we can imagine sort of taking this line and plugging it in. And we can do this for every edge. And then we get a graph where we have replaced the edges with a bunch of paths of different lengths. And now if we imagine some probability or flow sort of propagating through this graph, the kind of time it takes to propagate will depend on some sort of average of the lengths of these paths. So if all paths are long, then this will just take a long time. But if some paths are long, but on average they're short, then it will sort of not take too much time. Okay, but this is how you might imagine doing some sort of composition in graphs, but we want to do composition in general algorithms. Okay, but I told you any quantum algorithm, you get a line graph. So imagine a quantum algorithm that calls a subroutine, meaning that some of the edges in this graph correspond to, like, steps of the algorithm that are implemented by a subroutine. And what is a subroutine? Well, I claim that a subroutine is, there's one circuit for every possible input I, from which we can get one line graph for every possible input I, and these line graphs can have different lengths. So, I mean, if you believe me that for every algorithm there's a line graph, this should be no problem. And the idea is we're going to kind of take these lines and plug them into the edges of this graph. But you also might have noticed that it doesn't exactly fit. Like, there's a bunch of paths here, and only one edge here. And now, in something that I only have time to describe as magic, we're going to kind of pop this line into a somewhat more complicated graph that also can represent the algorithm. Please don't worry. Please don't worry about that. But then now you can see how we can sort of fit all of these lines into the edges of this graph. And then the important point is that we get one big graph where you can imagine, like, the sort of probability propagating through this graph, or somehow the flow propagating through this graph, will take a time that depends on sort of the average of these path lengths. So if they're all long, then there will be sort of a factor in the complexity. But if most of them are short, or their average is not too big, then the propagation won't take too long. So that's a very, very cartoon picture of how this works. And in my last minute, I would like to now just sort of state, in not a lot of detail, our quantum walk composition result. So first, something that probably everyone is familiar with. If you want to search n elements for a marked element, the complexity looks like this, where if Ti is the cost to check if the ith element is marked, naively we take a max over these. Often there's no variation in the Ti, and so we don't write it like this, but this is what you would naively get from Grover's algorithm. But it's known that this maximum can be replaced by an L2 average using something called variable time quantum search. And our quantum walk composition results are just generalizing this to quantum walks. So now I'm not going to go into details, and I'm going to state this in a way that's maybe only recognizable for experts who are probably the only people who care about these results on this slide anyway. So here's a kind of quantum walk called a Szegedi quantum walk. We get sort of a maximum over, here U, VV prime is the cost to take a step from V to V prime, and our result is to replace this maximum with a weighted L2 average, where the weight is something like the proportion of time a random walker spends stepping from V to V prime. And in another framework, the MNRS quantum walk framework, we also have a max over something called a checking cost, and we replace both of these maxes with L2 averages. And these are both special cases of sort of one more general result. But this is maybe all the time for detail that I have. So to summarize, we have this very general subroutine composition result that we can achieve if, instead of thinking about algorithms as like just a very strict sequence of gates, we rather think of them as like some more structured graph-like objects that, we can have the algorithm flowing through in a more fluid way. And we also have some composition results that are specific to quantum walks. And if you'd like to learn more, please refer to the paper. Thank you very much.
Okay. Do we have any questions? This one?
Thanks for the nice talk. Of course, you did emphasize that you only have time to explain this by saying it's magic, but let me just say that looking at the picture, it looks like you're making a number of copies of the circuit. So does this correspond to the actual algorithm in the sense that it uses more qubits than the original algorithm?
Oh, that's a good question. So no, it's rather that, you know, we kind of had like, each of these corresponds to a subspace with many dimensions, and we can then look at that subspace as being a span of a bunch of smaller dimensional subspaces. So here, we range over I and Z, and if we fix any particular I, we get a subspace like psi ti. There's one for each I. And then, so it's actually not a change in the algorithm, it's just a change in the graph. I mean, I guess there are multiple possibilities of a graph that could represent the same algorithm.
Right.
Yeah,
thanks.
There's another one here.
Hi, thanks for the talk. So the answer to my question might be yes, but I just want to check. So does your result generalize to the case where you have subroutines inside subroutines, and eventually to the recursive program?
Yeah, you could generalize this by recursing deeper. Yeah.
Thanks.
Thanks.
Okay.
Thanks. It seems like you're a bit measuring the time of the algorithm. So do you have some error that you lose because of that? Because I feel like if you can measure the time, then somehow it should give you more errors somehow.
Like, what do you mean you're measuring the time of the algorithm?
Like, let's say that for some specific instances, it takes 2 years instead of a few minutes to run this subroutine. Then if you execute your algorithm and see that it finishes in 2 minutes instead of 2 years, then it means that some of this instance that was long to run was not taken into account.
No, I mean, I guess like you shouldn't sort of lose anything. You would never probably run like so that you could never have terminated one, like, I mean, I guess if maybe it's simplest to see you would never, I guess, run so short that you didn't run one of the subroutine on some input that mattered, I guess, unless it was like a very unimportant input. I mean, okay, maybe you do lose something in the sense that this is all going to be bounded error, even if there was like no error in the things that you were composing. But it'll only be like some small probability of error, and you could also boost the success probability. Yeah.
Okay, thanks.
Okay. So let's take one last question.
Thanks. Yeah, great talk. Following up on the question before, is there any interesting story to recursion, like a function that calls itself, or a subroutine, like two subroutines that call each other? Can one say anything?
I have actually not thought much about recursion, just that, like, I guess by some inductive argument, you could recurse further, but if, I don't know about something weird like that, like a subroutine calling itself.
Yeah, itself, basically.
Yeah, I haven't really thought about that.
Thanks.
Okay, I know there are a few other questions, but because time is up, so please feel free to communicate with Stacey offline. Okay, thanks Stacey again.